We'll start the fifth class of Deterministic Network Calculus. So last class we saw some definitions on definitions of monoids, two types, commutative and idempotent monoid. Right. Then we saw definitions of dioid, commutative and idempotent. Where the idempotent diode was known as semi-ring. Um, then we saw what a complete diode is. Right. So these definitions were what we saw in the last class. We also saw and we also defined for a diode order relation. The order relation is given by if A is ordered with B. This implies A first operator B is equal to B. Right. Okay. So today we'll be looking at the min plus diode. So first, so to define a diode, you need to define one set. So a set and two operators, right? So you need to define this is a set, and these two are two binary operators. So first I'll define the set. The set for min plus diode is R min. So what is R min? It is the real numbers union plus infinity, right? So this is your set. And first operator is the minimum operator. So what does this mean is if you take A comma B belongs to R min, then A operator B is equal to min of A comma B. Okay. Similarly, we have the second binary operator as plus, the plus operator, which is standard, right? Like the standard addition. Now our plane is that R min plus is a commutative diode. Okay. So before going to show that this is a commutative diode, we'll just do a recap on what are the properties that a diode should have. Right. So that properties first. The set and the first operator should be a commutative monoid, right? Now for this to be a commutative monoid, what are the properties it should have? So this operator, the operator is associative and commutative, right? Next we have there exists an element in D which we'll call as the neutral element, such that any element in the set D, you get A operator with that element is A. You get back the same element, right? Now, for a diode, this neutral element, we'll name this as zero element. So intuitively, why it is named as zero element is something when you add something to it, it doesn't matter. It doesn't make sense. So 2 plus 0 is 0. So similarly in that way, it is zero element. But here, since the operator has changed, the 0 will not be your 0. So if you can just, if I can just give a coming up of what is about to come. So since this is a minimum operator, so anything you do in minimum with plus infinity, the number would be the answer. So a minimum plus infinity would be a. Right. So since your set in the min plus diode has an infinity, the neutral element here would be plus infinity. That we'll call it as zero element for the diode. Okay. So next we have D, the second operator. So this is basically the set D. This is the first operator, and this is the second operator, not the other way around. First operator is minimum, the second operator is plus. Okay. Next, this also should be a commutative monoid. Right. This commutative is only necessary if the diode is commutative. Because the diode is commutative, this should be commutative. If the diode was not commutative, this need not be commutative. But now since we have shown that it is commutative, we'll with the commutative. Okay. So we have the second binary operator is associative and commutative, right? Then there exists E belongs to D. This is neutral element for the monoid. But for all A belongs to D, A is equal to A. So now this element, we call it as the unit element, right? So here, why we call it as unit element? So since the second binary operator is something we denote to as a multiplicative thing. So anything, so if you add A into 1, you get A back. Similarly, we want something like that. But here the unit element is 0, not 1 for the min plus, because you add 0 to anything, it'll be come back as the same element. So yeah. Next, the third one is product is left and right distributive over less. We saw last time what does this mean. Then there exists epsilon for the second binary operator such that for all A belongs to D, you have A into second binary operator equal to. So this is known as the absorbing element. This absorbing element, whatever you do the product with, it will give rise to that same product. So these are the four things that you need to check to show that something is a diode, right? So now our claim is, R min and plus is a commutative diode, right? Okay. So we'll go one by one. So first we'll show that R min is a commutative monoid, right? So Yeah. So to show that, first we need to show that min is associative, right? So for all a comma b comma c belongs to R min, we have a min b min c equal to a min b min c, right? Similarly, I need to show R min is no, I need to show that there exists neutral element, right? So the neutral element here is, so no matter what there exists. So I know that um, plus infinity belongs to R min, right? And anything minimum plus infinity is equal to A. So plus infinity is your zero element, right? So the first one is proved for R min. So next we'll show that R min plus is a commutative monoid, right? So you have for all a comma b comma c belong to R min, a plus b plus c equal to a plus b plus c. This is something which you know. And now the neutral element is z. We know that 0 belongs to R min. Therefore, a plus 0 equal to a. Therefore, 0 is the unit element, right? So the fourth one is, so the second one also is true. Left and right distributive over plus. So plus is left and right distributive over min. So we can say that a plus b min c is equal to a plus b min a plus c. This is true. And b min c plus a equal to b plus a min b plus c plus c. These both are true, hence the third one is also true. Now we need to find the absorbing element. So plus infinity again belongs to R min. Anything you add plus infinity become plus infinity. So this is your absorbing element. Therefore, plus infinity is your absorbing element. Right. So what have we shown? We have shown that R min plus is a commutative dioid, right? With zero element as plus infinity, unit element as zero, absorbing element as plus infinity. Okay. Now we'll see what the dioid order is in min plus dioid, right? So when we say that, so this basically we are trying to find out the order induced by the dioid, not the natural order. So in the min plus diode, we'll see that 3 is less than or equal to 2 in the diode order because 3 min 2 equal to 2. This is what this is. And 3 min 2 is 2. So when 3 min 2 is 2, okay, let me write this the other way. So we have if A min B equal to B, this implies A is less than or equal to B in the diode order, right? So we have 2 min 3 equal to 3, which implies is equal to 2, which implies 3 is less than or equal to 2 in the diode order, right? So this is the diode order, but natural order 2 is less than or equal to 3. This is the natural order. So both the signs we differ by one sign is given by the Curly order and one is given by straight lines, right? So this is the diode order and this is the natural order. Okay, so next we'll go back to a remark. The remark is R min plus is not a complete diode because so for it to have a complete diode, it needs to have an element such that you have minimum of all x belongs to R min x. This we clearly know is minus infinity, right? But R min equal to R union plus infinity but R min equal to R union plus infinity. So it doesn't have any negative infinity, right? So what you can do is you can define a new set where you add plus infinity and minus infinity both. Okay. So now the claim is so R min comma min comma plus is a complete diode, right? Complete commutative diode. So where the zero element is plus infinity, unit element is zero, and absorption element is also plus infinity. Now the t that we are defining is minus infinity, right? But we need to define one more thing because what happens if you want to add plus infinity and minus infinity, right? If you want to add these things, we want to define it prior that this is valid. So in the normal context, in the normal algebra context, this is undefined, right? But if this is valid, then R min plus is an complete commutative diode, right? So one more way to obtain a complete diode with the minimum and addition operator is just to consider the R min plus. So you have the positive real numbers union the plus infinity. Now the T operator would become 0 and everything would remain the same. So this is also a complete commutative diode. Okay. So next we'll go into something of the diode of min plus functions. So any functions from R plus to R min, these functions so define the diode of functions, right? The operators that can be performed on these diodes are the pointwise on these functions are pointwise minimum operators or the convolution operators, right? Okay, so let me give you a definition of min plus functions. So we'll have f is the set of functions defined from the set of non-negative reals r plus to the complete min plus diode r min. Okay, so mathematically, when I write the curly script, I define this as function set of all functions such that it goes from r plus to r min, right? So now you know the min plus functions, right? Now we can define operators on these functions. So any operator on these functions. So one more definition is the min plus convolution. So let f comma g belongs to min plus function, the set of min plus functions, right? The min plus convolution. This also belongs to the set of um, min plus functions. This is defined by for all t belongs to r plus. So f convolution with g t is in 0 less than equal to s less than equal to e f t minus s plus g of s. I have these two definitions right here. Okay, so some remarks similar to the convolution that we do, the shape of the convolution cannot be defined, cannot be deduced, like cannot be deduced from the shapes of f and from the shapes of g, right? So, but intuitively, what you do is you slide one function. So basically, you slide one function along the other and take the minimum hull of this operation. Right, that is what you do. Infimum, here we have used infimum. Infimum and minimum are not same. So that what does it mean is there might not always exist an S such that um, F convolution GT is equal to FTS minus SGS. So we will discuss where in what cases does the infimum does not exist and what cases does the minimum is achieved. Infimum is achieved. If infimum is achieved, then we can say that there is a minimum. If there might be cases where infimum is not achieved. So then what we do, we will look into it in the later chapters. But for now, we'll start with some properties of convolution. So convolution is commutative, associative, and distributes over the minimum. So we'll let for all f comma g comma h belongs to the set of functions. So commutative f convolution g equal to g convolution f, right? So associativity f convolution g convolution h equal to f convolution g convolution h. Distributive distributive over minimum operator. So f convolution g minimum h equal to f convolution g minimum f convolution h. The last is addition by a constant, right? So for all k belongs to R, we have f convolution g plus k equal to f convolution g plus k, right? Okay, the commutative can get it from the definition of convolution. So the first one is done, right? Second one, associativity. So we need to write f convolution g convolution h. This is infimum of. So first we'll write the outer convolution. U plus v equal to t fu plus G convolution H V. How did we get this? So here we can write this as, so this equation as infimum u comma s greater than or equal to 0 and u plus s equal to, as you can see here, t minus s plus s. The argument of f plus argument of g will always give rise to t. That is something that you know. You're just shifting it, but the t remains the same. The amount of difference between the function value at of f and g, they are shifting, but the difference remains t. So you're using that to convert this into a infimum over two variables. So now you have f of u plus g of s, right? S is greater than t. Since s is greater than 0 and u also is greater than 0, you will see that u and s both varies from 0 to t. But if s is t, u is 0. If u is 0, s is t. So basically you're doing a change of argument for t minus s equal to u. That is what you have to do here. Right. Similarly, you get from this equation. So let me name this as some 2, this as 1. So this you're getting from 2. Okay. Yep. So now you expand the inside u plus v equal to t, and you have f of u plus inf w plus z equal to v, you have gw plus hz. Now, since fu, the argument of this fu does not depend on the variables the interior infimum is taking. Right. So what we do is we have infimum u plus v equal to t, infimum w plus z equal to v, fu plus gw plus hz. So since v equal to w plus z, you can write this as inf u plus w plus z equal to t, fu plus gw plus hz. Okay. Now similarly, if you start off with f convolution with g and g convolution with h at t, you will similarly arrive at inf u plus w plus z equal to t, fu plus gw plus hz. So you'll both arrive at the same place. So let me uh, call this red 1 and red 2. So from red 1 and red 2, we get f convolution g convolution h equal to f convolution g convolution h. So the second thing is proved. Now you want to show distributivity over minimum. So the second one is also done. Now we want to show distributive over minimum. Okay. So what we want to show is we want to show f convolution g min of h t. So again from the first we have infimum u plus v equal to t, f of u plus g min h v. Okay. Now, from the definition of monoid, we know that the the second operator distributes over the first operator, both on the left and right sides. Here the second operator is plus and the first operator is minimum. So we can write this as infimum u plus v equal to t fu plus gv min fu plus hv. Right. Now we can separate this as u plus v equal to t fu plus gv min in inf u plus v equal to t fu plus hv. This is basically f convolution g at t min f convolution h at t. So this also is proved distributively. Now the last one is addition by a constant, right? Okay. So addition by constant, what we want to prove? F convolution g at t plus k inf u plus v equal to t fu plus gv plus k, right? Since k doesn't depend on the interior, the inside, the variables of over the infimum, and k is a constant, so you can bring this in, right? Now we have f convolution g plus k. Okay, so yeah, these are some of the properties of the convolution operator that will be useful for us when we um, do min plus algebra on real systems. So today, what did we see? We saw that how the min plus diodes. We showed how min plus diode is a diode, a commutative diode. Then we defined something known as min plus functions, and we defined operators on those functions. The one of the operator defined was convolution operator. We saw some properties of the convolution operator, such as commutativity, associative distributivity, and addition by a constant. So next class, we will see more properties on um, we'll see more properties of convolution, and we'll see some more subsets of functions which would be uh, easy to define, and then we'll see surjective closure and clean star operators. Right. Some more operators on these diagrams. Yeah, next class we'll do that. Okay, I'm stopping the recording now. Thank you for